Spherical coordinates is the topic of chapter 7, and doing separation in spherical coordinates is quite a bit advanced. So chapter 7 is long and has lots of glory mathematical details, and I don't think we have time to go through all the details now. What I rather like to do in this video here is to summarize the most important steps to give you a good understanding of really what's going on. Then for the details, unfortunately, you would have to look at the textbook. So in spherical coordinates we have one radius, r, and then we have two angles, an angle theta and an angle phi. And then the transformation from the xyz to the r phi phi, from the xyz to the r phi theta is given right here. So our x is r cos phi sine theta, y is r sine phi sine theta, and z is r cos theta. Let me show you how this transformation works. So here are examples of spherical symmetries. So here this is a point x, y, z. And then you can also call this point with an angle phi, which is here, a radius r, which is here or there also, and an angle theta, which is the angle towards the z-axis. And the first thing you do is a transformation of the Laplacian, right? You remember the second derivative, the sum of the second partial derivatives, to transform this into r, theta, and phi. Okay, so this is done somewhere here. And so then here formula 7.1 would be the full transformation from xyz to r, theta, and phi for the Laplacian operator. And, well, this formula is involved, and to derive it takes lots of pages of math. What I like to do here is to look at the separation idea. And let me do this on a separate page. So in spherical coordinates we have r, theta, and phi as our coordinates, and then a function written in these coordinates will be separated out into a function which is radial, and then another function which I called s, which depends on theta, and another function q, which depends on phi. Okay, and of course now we would like to get individual equations for r, q, and s. And if we substitute this into, let's say, a heat equation with the Laplacian and spherical coordinates, we can do the separation, we introduce separation constants, etc., etc. You have seen the steps now many times. Let me show you what you get. So the radial problem becomes the following. So we get d by dr of r square, d big R by dr. So that's the second r derivative in a modified version. And then we have a mu square r square minus lambda times r is equal to 0. And here we use already two separation constants, the mu and the lambda. Well, we know that we should get 3 separation constants even, okay? So here we have 2 of them. And this is called the spherical Bessel equation. And then the solutions, of course, will be called spherical Bessel functions, and I come to those actually in the next video. The q problem, if you do this for the angle phi, will become q double prime plus nu q is equal to 0. Oh, so this is one of our standard problems. And then the s equation, which depends on theta, gets a very strange form. So this is now sine theta d by d theta of sine theta ds by d theta plus lambda sine square theta minus nu s is equal to 0. So that's the s equation, and so we have separation constants. Maybe I write this here. We had lambda, we have mu, and we have nu. So we have 3 separation constants. Okay, and so then if you do all your thing with your boundary condition and you find the corresponding sine and cosine or the corresponding spherical Bessel functions, or for S we find the Legendre polynomials, then you get indices n and m and k, and so then in the end you have lambda n and mu m and nu k, and you have to put it all back together. Now the S equation can be simplified by using a transformation. Transformation is to call x cosine of theta. And then as written in the textbook, if you do this, then you get the following equation. Then you get equation 1 minus x squared phi double prime. This is now the x derivative, the prime, okay. Minus 2x phi prime plus lambda phi is equal to 0. This is the Legendre equation, and then of course the solutions are called Legendre functions or Legendre polynomials. And these one we denote by Pn, and Pn of x are the polynomials, and then of course we transform back, and so the argument is then really cosine theta, which comes in there. This is enough for our little summary here. So on this page you have all the 3 important equations for this material. And let me talk about spherical Bessel functions and Legendre polynomials in the next video.